Hi, in this lecture I'm going to talk about LTE Advanced. Now, LTE Advanced, based on its performance, is the beginner of the 4th generation mobile communication technologies. So, it is highly advanced and it has many outstanding performance characteristics. What makes those performance characteristics possible? Well, ICIC and FFR, DSA, COMP, carrier aggregation, headnet and small cells, and self-organizing networks, SON, are some of those major features. And we're going to study about them in this lecture. First, ICIC, intercell interference coordination, and FFR, fractional frequency reuse. ICIC alleviates data rate degradation at cell edges due to intercell interference using FFR technology, fractional frequency reuse. Now, FFR separates the frequency bands and allocates the bands efficiently to prevent signal interference from adjacent E-node Bs, adjacent base stations. Looking at the picture that you can see down there, now you see multiple cells, and in the middle of the cells surrounding the base station is the green area. That's a frequency that we're indicating, which is the green frequency range. Then, near the edge of the cells, I have orange, red, and blue surrounding the edge of the cells. And these are different frequency bands, and they use different frequency power. As you can see in the picture way over there at the end, you can see that the power level for the red, blue, and orange are higher than the signal power that is used for the green areas. And that's a difference in power. In addition, different frequency ranges, different frequency parts are used for the blue, red, and orange, as you can see. And the base station will use directional signaling techniques such that surrounding its area, it will have the green area use the green frequency spectrum. In addition, when you look at the red, orange, and blue areas, you will have a directional antenna focusing on that area to use the right amount of power and the right frequency band to support it. This makes sure that interference is reduced. Why is interference reduced? Well, let's just take a look at this figure right here. Right down over here, you can see between the cells, right over there, near the cell edge, you can see a blue area, a red area, and an orange area are interfacing each other. They're side by side. And that's the part that is interfacing between local cells. It is blue, red, and orange, 3 different colors. These 3 different colors are 3 different frequencies. And because they're using different frequencies, their interference among each other is actually much reduced. That's what we're talking about, fractional frequency reuse. We are reusing the frequency, but we are fractioning it, as you can see, blue, red, orange. We're fractioning the frequency range, and we're using it in a special coordination mechanism in between cells to reduce interference. That's what we call ICIC and FFR. The next technology is DSA, Dynamic Subcarrier Assignment. DSA is an approved resource allocation scheme upon static allocation. And we're talking about actually SSA, which is Static Subcarrier Assignment Technology. DSA is a Dynamic Subcarrier Assignment Technology that is an improved one. And what it does is dynamically allocates subcarriers considering channel state conditions. In other words, if a certain spectrum is better in a certain range, as you can see in the figure next to me, there is a red line which is going up and down based upon the frequency range, and then there's a blue line which is another subcarrier that is going up and down based upon the frequency range. The idea is to use the right spectrum where that spectrum will enable us to perform better. So in the area where the red spectrum has a better performance, then I'm going to use the red. In the area where the blue spectrum performs better, then I'm going to use the blue spectrum signal components. This is what we call dynamic subcarrier assignment technology. Now, due to frequency selective fading, subcarriers have different effect on users in different locations. Thus, DSA can improve quality of service based upon its technique. The next technique is COMP, which is coordinated multiple point. COMP improves the coverage of high data rate, cell edge throughput, and system throughput. COMP coordinates multiple base stations, multiple eNode Bs to communicate with a user equipment, with a smartphone. Increased throughput by reducing intercell interference is accomplished by COMP. Now, COMP technologies include CS, which is coordinated scheduling, CB, which is coordinated beamforming, JT, which is joint transmission, and DPS, which is dynamic point selection. These four major COMP technologies. Now let's look closer into these four technologies of COMP. CS allocates different subcarriers to UEs at the cell edge to avoid intercell interference. And as you can look at the figure over there, coordinated scheduling, CS technology, is shown. Based upon where the mobile device is in the cell and over in the other cell, different frequencies, frequency 1, 2, 3, are different frequencies that are assigned based upon the location of the mobile device. And that is what you do in coordinated scheduling. The next one is coordinated beamforming. And in CB, what CB does is that it allocates different beam patterns to user equipment at the cell edge to avoid interference and improve reception performance. And as you can see, some signals that may create interference are nulled where the right signal is found and it's used in beamforming patterns. And that's what CB is about, coordinated beamforming. The next one is JT, joint transmission. JT improves the reception performance by receiving data concurrently from multiple eNode Bs, from multiple base stations. And as you can see, there is one arrow that is the stronger arrow, the larger, thicker one that is connecting to the mobile device. And it's larger because the mobile device is in that base station's cellular range, where some assisting signals come from the other base station over there and are connecting it to support joint transmission technology. Then comes DPS. Now, DPS is dynamic point selection technology, and it selects the TP, the transmission point, with better channel quality to improve the reception performance. And that's what is done over there in the figure below, where dynamic point selection is selecting among the signals from the base station to make sure that the performance is optimized. Comparing these four COMP technologies, we can look at the resources, number of TPs, decreased interference, and reception performance. And as you can see, in CS, it's about the resources is the frequency. In CB, it's frequency and spatial control. JT uses frequency and spatial control, and DPS uses frequency, time, and spatial-based control. Number of TPs, well, in CS, it's single. In CB, it's single. In JT, it's multiple. And in DPS, it's multiple. Decreasements in interference, well, what happens is that CS and CB do show decreases in interference. JT and DPS may not provide that level of performance. Reception performance, well, CS is one that is not as good as CB, JT, and DPS when it comes to reception performance. These are the references that I used on LTE Advanced, and you may be able to use them for further studies on this topic. There are 3 more techniques that I need to talk about that are key techniques in LTE Advanced, and I'll do that in the following lecture. Thank you.